Welcome, everybody, to the 9th installation of the Dr. TLA Plus series. It seems we are arriving at an annual episode, one episode a year, so it's good that we don't do cliffhangers or something. In good tradition, today will be about Paxost, so that's, I think, the 5th time that inside of Dr. TLA Plus we talk about Paxost. Everybody should be familiar with Dr. TLA Plus now, I guess. So today we have a chance to look more at proving TLA Paxost correct with TLA Plus. And Chaksam, who's a soon-to-graduate PhD from Stony Brook University, New York, will show us what he did, taking Leslie's specs, amending Leslie's specs, and then the tricks he found out that make it easy to prove Paxost, Multi-Paxos with TLA+, the proof system.
Hi. Oh, I have a mic. Okay. So what I'm going to talk about is, first we will talk about specification and verification of Multi-Paxos in TLA+. And then later on, in the second half, I will try to talk about using history variables to specify these algorithms and using these specifications as a tool to generate invariants, although manually, but you will see that it's very systematic. It's a kind of a method to generate invariants, which is pretty tough when it comes to these systems. Okay, so just some background first, which I think everyone know. So we are going to look at distributed systems. It's a set of processes with communication channels. Processes communicate by message passing. Processes can crash. They can later recover. And in the specs that I'm going to talk about, when a process recovers, it somehow knows all of the state that was before it crashed. It doesn't lose the state. So you can think of it that everything is stable storage right now. Okay. And as far as messages are concerned, messages may get lost. Messages can get duplicated. They can be received out of order. For example, here, M5 and M6. And they can be delayed indefinitely. Now, so what we're going to talk about is Multi-Paxos, which is an algorithm to solve consensus. Consensus is that processes need to agree on a single value. So in here, they want to agree. There are 5 processes, and each process is claiming their own values, and you want some kind of consensus. So here, they all agree on C. Multi-Paxos solves multi-value consensus, which is about agreeing on a sequence of values. So here, they're all agreeing on some sequence. And it is not the case that there is some process which is proposing this whole sequence. Processes are proposing parts of the sequence, and somehow we just have to make a sequence. Okay, so you assume that they are independent. Yeah. So the properties that we want to talk about when it comes to distributed algorithms and in general are safety and liveness. We won't talk about liveness today. We will only talk about safety. And safety for consensus is just that if 2 values are chosen, then they have to be equal. Okay? This is for single valued. In multi-value, you just do it per slot. And to solve actually consensus, there is a huge literature on solving it. There are many algorithms. We are going to focus on mainly 7 and 8. Yeah. But there is a huge literature when it comes to consensus algorithms. No. So I'm not going to really talk about Paxos and explain Paxos. All the information that you basically would need about it is that you have 2 kinds of processes, proposers and acceptors. proposers propose some values, and acceptors vote on these values. And when there are enough votes on it, on some value, that value will get chosen by the system. Okay. In our specifications and proofs, we assume that there is a quorum set Q. Oh, this looks very funny, but this is a Q, and it's some subset of the power set of acceptors. And what it's saying is that between any two quorums, there is at least one guy in common. So their intersection is non-empty. Okay? We use this as an assumption instead of actually having quorums and then proving that this is true. We use this as an assumption directly. Okay? Yes. You can prove it, but you would need linear integer arithmetic to do that. But anyways, right now we'll use it as an assumption. And when it comes to Paxos, it's basically just a two-phase algorithm. In the first phase, the system tries to do leader election and state consolidation. So basically, the system tries to pick some person, some process, which could be a leader, although it's not explicit in the sense that no process becomes a leader. It is silently a leader. And this process will try to consolidate the state of the system in the sense it will ask everyone if they have voted for values, and it will try to determine if something was chosen or something has to be done, et cetera, et cetera. And once phase 1 succeeds, the system will enter into phase 2. And there, actually, whoever is the leader or whoever thinks he's the leader will try to do consensus and replication. This is Lamport's English description of Paxos. We will come back to this later, but I wanted to show how it is very concise. It's very beautiful. And what Lamport did was he wrote a TLA spec of this, which is this, where each action is corresponding to one bullet point in this English. And this was done by, I think, Lamport, Mars, and Doliges. Okay. Although I think the spec itself was just written by Lamport, but I'm not sure. So what we will do is to use this as a template and generate multi-valued Paxos out of this. So this is just for single-valued, and we'll try to get multi out of this. And we want to minimally extend it, because the idea is that I want to show that you can actually reuse a spec. It's not that you write a spec, you prove it, and then it's just done, and you never touch it again, or it cannot be touched again. The idea is that you can actually work on these incrementally. So that's what we're going to do. And that brings us to the formal verification of Multi-Paxos for distributed consensus. So what we will look at is the complete formal specification in TLA+. I will focus only on the specification, not so much on the proof, actually. I will just briefly talk about it. And finally, we will see how to extend even this specification with more actions and properties. Okay. So the way you can get multi out of basic is basically just to add slots to your whole algorithm, right? So one trivial thing that you can just do is to basically take the whole algorithm and just repeat it for each slot, as in for each slot in the sequence. For each one, you can just repeat the whole algorithm again. Although that is not what is Multi-Paxos. That is one way to do it, but it's horribly inefficient. And the difference between this, what I just said, and Multi-Paxos is just that the first phase is done only once, as in leader election is shared, but phase 2 is done per slot. Okay? Because leader election has nothing to do with slots and anything. But when you add these slots, what would basically happen, these scalar values or these numbers, so if you have some one number, it will become a pair, like a value slot pair, valid slot pair. You will get tuples basically. And so scalars become vectors, sets of scalars become sets of vectors, and records of scalars becomes records of sets of vectors. Why this is important? Because this completely changes the proof. While for basic Paxos, the proof is pretty, it is challenging, but it is smaller and still not as bad as the proof for safety of multi-Paxos, because you have to deal with a lot of things which the theorem provers actually find difficult. So you have to manually make it convenient for them to carry forward the information. So now what I'm going to show is the 4 phases of multi-Paxos and how I got it from basic Paxos. Right? So phase 1A is a proposer is just proposing some valid B where he is trying to become the leader. So the only difference between these two is just that now I'm just storing this B in a variable. That's it. But other than that, there is no difference between this spec and that spec. Okay. When it comes to phase 1B.
Could you go?
Yeah.
So there's the check there that there does not exist MN messages such that ballot's already used.
Yeah.
So this spec kind of like assumes that
it's globally
has
shared.
like
Everyone can access
visibility
it. Yes.
of all the messages?
Yeah.
Okay.
Yes. Although you can, so in this spec, actually you don't need this here at all. You need this in phase 2A that we will see in the future. But even if there, I will come to it later. It will become easy there. Yeah. Right now, let's put a pin on this. But yeah, it's globally accessible. Everyone can see the entire message history. Yeah. And again, I could change this, but that would create a change which is not relevant to what I'm trying to do here. Because then I will have to do a change for this. So I didn't want to touch that. And then phase 1B, what basically happens is that because it has to do state consolidation, so the acceptors, when they see a 1A message, they reply with whatever they have voted, okay? And rather the maximum of whatever the most recent thing they voted on. And the only difference here is that it would be not just a value and a ballot. It would be a whole set of ballot slot value pairs, because now you're doing on each slot. But that's the only difference. The rest of the stuff is not changed. And when it comes to phase 2A, this changes, it looks that it changes drastically, but in principle, it's almost the same. So the whole structure is the same thing. And here also, you note that the first line is the same as phase 1A. Okay? And apart from that, what basically here it is specified is that the proposer receives a quorum of messages, 1B messages, okay, such that either in all of those messages, nothing was voted on. And in that case, you propose any random value, V, because it's just this. Otherwise, you pick whichever is the most recently voted value, and you just carry that forward over all the set of messages. Okay? And what we are going to do is basically just do this, but per slot. So we just do it with, So we just change this. Basically, we are just taking this here, instead of proposing one value, it will be the set of slot value pairs. And propose would be, it's either a value which has already been voted for, or it would be a new value, okay, on a new slot in the sense. So max SV, this basically is this disjunction. Okay, so if something was already voted for on some slot, so just carry the max of that forward. That is what this guy checks creates. And new SV is because you can propose on a new slot, and that is what this guy does, and that is what this is. And this is corresponding to this guy, the first disjunction. That's it. Yeah. And finally, for phase, that should be 2B. For phase 2B, what we're doing is, again, it's the same as phase 1B, but instead of just replying with the same ballot value, you just reply with the whole set. And you update, instead of keeping just 2 values, you're updating the whole set. Okay? And now if I come back to your question, if you can actually remove this conjunct from the entire specs. The only difference is this has to be greater than. And then it would be fine.
So I know that many implementations, they assign each acceptor a rank. And so the ballot is actually rank and number.
Yes.
So
that is another way to.
Another way.
If you do it that way, that would ensure that this will be true, right? And then you can have greater than equal to, but you can actually just use a number. But then this has to be greater than, because if it is equal, it can vote again, which is wrong. So you just make it greater than, and it will still be fine. Yeah. But in this spec, I didn't change that. And also, another reason I didn't remove this, was also because it's a known way how to do that, so I didn't really bother. And when it comes to the proof is just the usual hierarchical style of proofs. We write from the specification, we will say that the specification implies a bunch of invariants, and these invariants would then imply safety. And then the proof is it's a hierarchical proof by induction for each action, and then for each action, each invariant. That's it. Nothing complicated there. But it's just that the proof is much more complex because we have more complex data structures now. So in terms of some numbers, for basic Paxos, the spec size, in fact, if you see, it's not that drastically different. Okay. Proof size is, however, very different. It's a 150% increase. Number of obligations is also almost doubled. Why is this there? Okay. And proof check time also increases a lot. And all of this is mainly because you have these blown up data structures, and also because I'm using a max operator. So I have to write a few lemmas so that the provers can understand what the max means. That's because TLA doesn't have a max built in. Yeah, so I have to write on my own. We won't actually go into this. This was actually because I did also extend this with preemption, which is in which preemption means that if a proposer realizes that his ballot has been overtaken by someone else, it can start a new ballot. So here we actually specified that also clearly with just extending from this. There, the spec increases, but the proof doesn't increase that much. The time seems to increase because I think there is something with the in TLAPS that if you import a new library, it drastically increases the time, even though if you're not using anything from that library or module in the sense. So, yeah, which was weird. In the sense, and I realized it because if I just import it and not use anything in the proof, it still increased the proof time for some reason.
What's the library you needed to use?
Finite set theorems.
Finite set, okay.
Yeah. And again, I need finite set because of just the way I proved it. Maybe there is another way which doesn't need that particular module. So after this, the point was, can we make the specification better? And more importantly, can I do something so that these invariants, which I didn't talk about, can be more methodically generated? Okay. And that's where I thought of using history variables. That's fine. Oh, okay, that's okay. And that brings us to the second half, where what we're going to do is to look at these specs, and we're going to specify them with only history variables, and see how that helps to methodically generate invariants or follow invariants from the spec. That's what basically the slide says. As case study, I will do single value. We did single value Paxos, multi-Paxos, and the preemption, which is from the previous slides. And I think I will only show single value Paxos here, because I just want to show the principle. The exact same thing is done for multi-Paxos as well. Okay? Yeah. But for the sake of simplicity, we're just going to see this with single valued Paxos. And result-wise, the specs decreased almost by a quarter. Proof size decreases again by like 35%. But more importantly, I needed fewer invariants because of the way I wrote it. And proof check time obviously would decrease because it's a smaller proof, fewer invariants, so on and so forth. And regarding this one, we were able to actually at least methodically generate all of the invariants except for one guy. Yeah. So we are going to see these other ones and not the one guy. I will try to discuss it at the end. And although we couldn't get that one guy, which was used in the original proofs by Lamport and by us, but I can generate something else, which you can use again to prove safety. But that is not very methodical. It has, it's a bit hacky. I'm doing it more manually.
Do you know any impact on finite model checking? Like, did you try to default?
It will be horrible because because now we'll see the specs why it will be extremely horrible. So just to introduce this. So when it comes to just TLA, not spec, or not just a TLA spec, but anything, you can basically think about that in distributed algorithms, you have two kinds of variables. One is a history variable, which is the set of sent and received messages. And you can have something which we are calling as derived variables, which would be basically any local data which is maintained by processes, usually for efficient computation. So if you are taking max of something from some set of messages, you will only always maintain the max. So in that sense, the max is a derived variable. Okay. So, but what we realized is that these derived variables are obviously a function of history variables. And in all the distributed algorithms that we see, there is only a few functions, like it's max, sum, count. We don't have a lot of crazy kinds of aggregate queries, etc., when it comes to distributed algorithms. And that's why it could work. So as a result, what we do is, let's write the specifications just using history variables. Don't keep the derived variables at all. So now, what we're doing, we're writing basic Paxos. And what I'm basically doing is I'm writing it from the English, which we saw in the first, like in one of the slides earlier. I'm writing the spec from the English, and I'm comparing it with the existing spec. Okay. So first, he's just saying, selects a number, sends a message. So that's basically what you just send the message. So you realize that this is actually not said in the English, and you don't really need it. For phase 1B, similarly, it's the same thing, but it's more complicated. It looks complicated, but it's not really. So when an acceptor receives a 1A request, so you receive some 1A request, and the val is greater than that of any 1A request to which it has already responded. That is basically this aggregation here, that m.val is greater than anything that it has responded to. Then it responds to the request with a promise, which is a 1B message, not to accept blah, 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 and with the highest number proposal that it has accepted. So we send this promise, and we calculate whatever would be this highest number proposal, and that would be this R. That is what this operator is doing. Okay. And the highest numbered proposal is that it has accepted is over the set of all 2B messages. You just see whichever is the most recent one, whichever has the highest ballot. And that's what basically all we're doing. And we're trying to follow his English, not this, not the existing TLA spec.
So if we look at this, like this is looking through the entire history of sent messages.
Yeah.
If we were to like try and translate that to like how it would be implemented in real life, there would actually be a derived variable that would basically have that for us. And so like in an actual implementation, it wouldn't need to look through the whole history. It'd have the derived variable. Is that correct?
Yeah. So in the actual implementation, you will actually just have the derived variable. You will actually not have the history. And that derived variable is basically what Lamport actually wrote in his spec. But if you look at from this, you can actually, at least methodically, figure out what the derived variable should be and how to update it. And you can just take the spec. You can do that. From this, you can get this. And once you do this, you know that you don't need sent anymore. Because in this spec, the only variable was sent. Once I do everything derived, I don't need sent anymore. So I can forget about sent. I only need these then. So this gives you one way to, from this, how do you figure out what should be stable storage? You can forget sent, and you get, basically now I know that this is the stable storage. Yes. Yeah, that's the trick. Yeah, okay. Similarly, you do it for, I did for like phase 2A and for phase 2B. Yeah, they are similar to this guy. Here, this is the most difficult one. The others are pretty straightforward. So let's just skip them. Now, let's talk about the invariants and how to figure them out. So again, if you take a distributed algorithm and it has two kinds of variables, derived and history, if you're writing the invariant has to be written for some variable. So you can basically just have three kinds of invariants, one for derived variables, one for history, and then type invariant. Right? These are the only three kinds of invariants that you can write. Right? In our case, because we don't keep these, so this whole chunk goes away. So you just have to have type invariants over the messages. And you just have to figure out what should be the message invariants now. And that's it.
Right. But I don't understand in the original approach, why don't you need invariants that relate the history variables to the derived variables?
You need them.
You do?
Yeah, you need them in the original, yes. Here, you don't even need those. Okay, so obviously the advantage should be, since there are no variables, you have fewer invariants, and you can kind of systematically derive these guys, except for one. So just to give like a brief intro, how I derive it, it's very easy. Basically, for each action, you just look at what is the message it is sending, okay, and look at whatever is the increment here. Okay. Then you basically just kind of map the values in the new message to wherever they are coming from in the action. Okay, just make a link, like in your mind, And finally, just assimilate it. And the assimilation is basically going to create the invariant. Here, I'm going to explain it better now. So let's see the example. This will be much better. So for example, if I have to generate this 2B message invariant, what I'm going to do is that you take the new message, whichever was generated. In this case, this 2B message. Now, here you have that ACK is A, which is this, and bal and val are m.bal and m.val. And m is some 2A message, and I'm just copying its contents. That's it. So from that, I can write that for this particular message, for this particular 2B message, there must exist a 2A message with this. Right? Pretty easy. And if this is the only action which generates 2B message, then I can say for all. Right? Pretty simple. Yeah, very obvious.
So here you're sort of saying that the set of messages is going to be a fixed point, but not the least fixed point.
No. No.
So you're going to have to add something else, right? Because it can't be any fixed
and that,
point. It can't be the set of all possible messages which would satisfy all these conditions.
No.
Okay, I got it.
So sent is actually a set, not like an ordered?
No, it's a set.
It's a set.
No, set, it's just a, so the sent is just, it's a set which is monotonic. So you can only add to it, that's it. You can't delete from it, you can't modify its contents. No, you can just add messages. So it's, in that sense, it's actually it's not like the sent received message queue of the processes. It's a theoretical sent, that I sent this message. This is the same in Lamport's.
Right. I mean, really, in a way, this is just re-encoding.
Exactly, yeah.
And
that's why I'm saying that you can methodically, you can even automate this, but I just didn't because we're doing something else. Anyway, so this is one kind. This is a very simple kind of invariant that you can generate. So this is one kind, which you can generate for each possible time.
Actually, this is the horn logic encoding.
Yeah.
Algorithm.
Yes. For 2A messages, again, I can generate the same thing, but so I will not show that one. But we need a different invariant for this too. So here I'm saying we see this B, and where is this B getting used? Right. So I see that there's this one conjunct in which this B appears, and can I somehow combine? Can I get something? Can I encode this information in the invariant? That's basically what I'm trying to do. So in this case, what I'm saying that for each 2A message, based on this, if there is another, what's trying to say that if there is another 2A message with the same ballot, then they have to be the same message. So this is something which is a bit more manual than the previous one. Previous one, you were just copying things. Here, you are not really just copying things.
So how is the B selected when it's...
Oh, it's just
doesn't it, I guess... Wait, doesn't it matter how the B is selected, or does it not?
In real implementations, yes.
No, just in this, actually.
No, B is just a parameter.
Yeah.
So it doesn't matter how it is selected. It would in my next, it's just there exists a B such that phase 2A of B is true. So it can be non-deterministic.
Oh, this is a phase 2A. Okay, yeah, sure. Yeah.
But so before when you had exist, it's fine because sent only increases.
Yeah.
But here the for all, so in this case it is an invariant, but it doesn't have to be in general.
No. It's that's why I'm saying it's more manual in this sense. It's not that I can directly copy. No. Because this has negation.
It can be copied, but it doesn't have to be.
No. Yeah. It's the negation is what's making it that. Yeah. If there was no negation, then you can probably do something. But even then, there will be some additions, which we will see in a later invariant.
What do you mean by negation?
Huh? Negation.
Okay.
Because negation usually complicates things. because in general, negation just means that right now, when you did this, then something is not true. But you don't know in the future if it will become true. Yeah. So you basically, if you want to add something like that, you just need to add another parameter here that for every time which is less than this is true. That's it. Which we will see in the future. We actually have an invariant for. We need an invariant like that. And now we go to 1b. So the first is actually the same as the 2b one, where you're just copying things. So here, in your 2b's, so you're selecting this R from this, and this uses this, and there is a disjunction here. So in the same way, I'm going to have a disjunction, and I'm saying that for every 1b message, I'm basically trying to figure out what is this max vval, max val, okay? Because the other things are common. And I'm trying to figure out something about that. So either this is true, in which case this would be -1, or it has to be something in this set, and this set is this set. So I'm just copying the parameters from that definition. So this one is easy. And this is a slightly complicated invariant, because here I will generate an invariant using max, in the sense that here, this guy, it's actually taking the max of some set. Right now, I just did a copy. Now I want to propagate this information that it's a max. So that I need to write an invariant of. So to write that, what I'm doing, so because it's a max, so it has to be, it would ideally be, I would have the invariant over all the values which was after max. What I'm trying to say is, so if you take a max of a set, right, you're saying that the set has that, its upper bound. So after that should be nothing. That set should not have anything which is after that. Right. So here.
What's that syntax you have? The second line.
This is mathematical. As in it's a mathematical set. Oh, it's a range.
It's a range.
A range.
Oh, okay.
It's math. Yeah, it's not a TLA.
Okay.
Because it was just for simplicity.
Sure.
Yeah.
So these are two natural numbers, and what's
exactly.
the range between them?
Yes.
Okay.
So here, basically, I'm saying, first of all, what was the max? In this case, it was stored in here. So this would be my the point after which nothing should exist. But that is only true right now. So this next part is basically telling that the max, after this should be nothing, but it's right now. And this part is telling what should be right now. And that is from here. This is something which is pretty manual. You have to, because for this, you have to know that this ballot is kind of like it's a time, or it has some kind of total order. It's basically, that's how the algorithm is using ballot as. Okay?
What is A in this context?
Acceptor. It's some acceptor, A.
And .acc equals A, that's in...
Oh, that's the sender of this message is A.
Oh, okay.
Yeah, it's a from.
It's like a from,
Yeah,
okay.
but in the original spec, it was called AX, so I don't want to change. Though I can. So when it comes to max, what I'm trying to say is that after max, nothing should happen. But it's only true for right now. So you will basically get a range. And in that range, you know nothing should happen. And this nothing is, in this case, that you are taking a max of 2B messages. So you know that between that, there should not be a 2B message such that this is true. And its time is in this range. Right? And that's basically, you get this invariant. So these are the 4 main invariants. And these are the 4 that I could kind of methodically see how to generate. And beyond that, there is one guy, which I cannot generate that one. I can generate something else, which I can probably, if I have time, I can show. But let's see. So right now, I'll try to summarize this part, that what we're basically trying to do is we are trying to discuss the formal specification and safety proof of this using just history variables and trying to see how you can use this to at least manually, but methodically generate these invariants, right? And yeah, these are, in fact, these four, these are all the invariants that you actually needed in the original proof, except for type invariant, and the one which we cannot generate right now. Okay, thanks. Okay, yes. Oh, awesome. Oh, 11:45. Oh, okay. Oh, okay. And okay, so now I can actually kind of show the one thing that cannot be generated right now. Let me go into some slides. Oh. Actually, I can just show it in TLA. That's easier. And in fact, the reason we cannot generate that one is this it? Oh. So the invariant which we can't generate is this guy, which is over 2A messages, that for every 2A message, the value and the ballot that it proposes, this predicate safe at is true at it, where safe at is defined like this, and it basically is trying to say that for every ballot, B2, which is smaller than B, either there exists an acceptor which has voted value V at that ballot, or a whole quorum of acceptors have promised that they're not going to vote on that ballot. This is something that I was not able to generate, but what I could at least slightly manually generate was that instead of going this whole set, you can say that between the ballot, again, going same by the, because 2A also has a max. So if you again exploit the max of the 2A, because in 2A phase 2A also the proposer takes a max. So what you're trying to say there is that whatever ballot that B, which this proposer proposed the value on, okay, and whatever is the max of all the 1B messages that I received, between that, there is no value that can be chosen at all. So it's kind of extends. So it is something like, let me go back to the slides. So it is basically this same thing. Okay, the difference is that here this is true for one message. You're taking it for a message, whereas in phase 2A, it's for a whole quorum of messages. So it would add that quorum aspect here, and what it would say is that this range would be whatever is the ballot on which the 2A message is proposed, and the lower bound would be the max of the 1B. With the received 1B messages. And in between them, you can prove that there is a quorum in which everyone has promised that they are not going to vote in that ballot. So instead of generating...
When you say promise that they're not going to
1B
vote,
message.
What does that mean exactly?
Oh, send a 1B message.
A 1B message.
Yeah. Oh, yeah, just this. This is a promise that... so this message says that I'm promising that now I will not accept anything less than this ballot.
Yes.
Yeah.
That makes sense.
Yeah. And so instead of generating this, which is trying to say for every ballot which is smaller, something is true. What I'm saying is for this, that between this ballot and the max of some 1B messages, between that, nothing was chosen. And at that max ballot, something was chosen. And that something has to be V. So this is talking about the entire ballots, everyone which is smaller, whereas when I do my stuff, I will only talk about B, the last one on which something was chosen, or something was voted, and between them, nothing can be chosen. So in timeline, is there a marker? Oh, there they are. So what I'm trying to say is that while this talks about the entire range of 0 to, say, B minus 1, we are going to talk about some point which is B2. And between these, I can say that nothing can be chosen. And if at ballot B, you can choose V, then at B2, it has to be V2. It can only be V. Can people see this? Okay. And in a way, if you keep doing induction, and if you keep moving this backwards, backwards, and backwards, you will realize that once you integrate it, you will basically get this guy. So this is basically a kind of differentiation of this. And if you just kind of integrate it, in a sense, you will basically get that. But I don't know how to do that integration at all. Yes?
So when you say you don't know how to do this, like you haven't managed to prove it in TLAPS or
Oh, no, on paper. I didn't,
on paper.
Because this much I can at least methodically generate. And using this you can prove safety. The proof is different because obviously the invariant is different. So the final proof, which would be this guy, this would be different. Because this guy assumes that SafeAt and it's getting these guys, these 3.1, 3.2, 3.3, they're actually coming from the definition of SafeAt. In our case, I don't have that. I will have something like this.
So you're saying in the future you would want to weaken this assumption? This is an assumption you're taking? Or?
Oh, no, this would be an invariant. This is an invariant.
Okay.
This is This is the invariant which can replace this invariant, but would still give you a safety proof. Yes. And the plus side is that because you kind of methodically generate them, you know what the proof is going to be. So if you can somehow automate the whole thing, you don't need to prove this. Because since you know how to generate it, you know the proof. You only need to write this part. Yep, just this, this much. This is what we would be left with to do, which may be also automatable, but I didn't think that.
So it's definitely attempt to define a slightly different invariant that is closer to what you can generate methodically.
Exactly.
That's what you mean?
Yes.
But with that invariant, did you also prove it? I mean, I understand.
Yeah. Oh, yes. Yes, but unfortunately, that proof is in my work machine.
No.
Yeah.
So I think just that answers your question. I think you do manage to.
Oh yeah. It does prove
right,
it.
just that it's not.
It's a different
generated methodically.
Okay.
So
And generate methodically, you mean like translating from, let's say, spec to the history spec? Is that what you mean, generate methodically? Or what?
No, just from my history spec to generating the invariants from my history spec.
Oh, right. Generating the message invariants. What we've been talking about.
Yeah.
Yes.
Lamport's spec is out of the picture
Yeah.
at this point. Yes. Yeah. And kind of the motivation of doing this is that because we have a language called Distalgo, which actually executes, in which you can specify. It's a very high-level language for specification, but it also executes. It translates to Python and can run Python. So the trick was that if I write a high-level spec, which is just using history in Distalgo, it will execute. I should be able to do a translation in TLA because they are so high-level. It's like a line-by-line translation. I can prove this TLA spec, and that would therefore carry forward the proof to an executable program, as long as you trust the translation. And even in Distalgo, even language or as method, if you can also write a compiler which can take these queries in Distalgo and generate the derived variables, then you actually get an executable code which is more efficient, because in this case you are every time taking max of a whole set, so it's an ON query, whereas if the compiler understands something called incrementalization, it can generate that max query into just a single O1 operation, which is just create the derived variable and just maintain it every time you see something which is going to update the set, and that's it. So the whole pipeline was that you can actually prove something in TLA Plus of an executable program, which is initially written in high-level queries, and if you use a incrementalization compiler, it would actually also generate an efficient code. So you're actually transporting the safety argument from your TLA Plus spec and proof to an executable, efficient code in that sense. Yes. That is basically the motivation of doing that. That's why we were so bold enough to write just using history. And also, to come back to your question, model checking will be tough because you're taking max of a whole set. So when the model checker, every time the model checker has to execute this whole query, whereas in the earlier spec,
well, that set doesn't get too large, does it? Or
maybe not this one, but then this one could. No, this one is not. No. So it doesn't get that big, but it will still get bigger, especially for multi-Paxos, because then you will have, it's a set of triples and everything.
But there's not going to be like a combinatoric explosion versus the regular spec or anything, would there? Like there'd just be like maybe be like twice as slow or something, but it wouldn't be like a million times as slow?
No, it's not exponential, linear, because it's O1 to O1. But that is per action. So I think if you're trying to calculate for the whole, no, it will still be linear with comparison to the,
I'm also interested just in like comparing the norm, like I've always written specs as like I'll use derived variables and even consider this whole history, right?
Just
thing. Does the one like refine the other? Like how is that relationship? Does the history one like refine the derived variable one? Or?
I think you can in principle, but I don't know if in TLA Plus you can do it.
It's just kind of like they're equivalent in different ways.
They are equivalent,
right?
yeah.
Okay.
Exactly, yeah. So there should be a way.
Subjectively, would you say that specifying a protocol using like history variables is easier than using derived variables?
It actually depends on where the spec is coming from. So here I was specifying using his English, Lamport's English, and he doesn't use, in his English, he's not using any derived variable. It's just send messages. So it was very straightforward. But if the English and the pseudocode, they have a lot of these variables, then you have to be smart enough to make the translation, do the reverse of that.
Yeah, that would be my question. I just checked the raft specification, and I think it has about 14 different variables.
Exactly, yes.
How difficult do you think?
I don't think it is that, it won't be that tough as long as they are, because they were also, they're also maintaining some aggregate queries. They're like max and counts and stuff. So in that sense, all you will basically have to do is just say change something called, if the variable is max, say val of A, to just max val of A, make it into a predicate, and this predicate would just be whatever is the max in the set. So in that sense, when it comes to, you can just take that spec, you should, in principle, only have this much change, and you have to write this. But for this, writing this thing, it has to be like done by a human, yeah, because we don't have a system which can do that reverse.
What about reading the spec? And in your opinion, like, given a spec written in the derived variable style versus the history style, like, which as an implementer do you think it would be better to read if I were to take the spec and write it as an actual system?
I like, it really depends. So with one problem with using derived variables is that it will appear somewhere, but then it's updated somewhere else, and can be updated in many, many places. So in that sense, when you look at an action, you don't really, just looking at it, it becomes tough to know what is it doing. So, but if you write it like this, then it's just, because everything is just there. You just have one variable and you wrote the whole thing. So you know what it is doing. So in that sense, I like it, because I can understand the thing better, and I can understand these actions individually much better. But if you have, if you have derived variables, if you know that what this means, I mean, it would do the same trick. Yes. But the thing is, again, like for example, for Raft, it has like 14 variables. Some else will have like more. So keeping track of all of them and remembering what each one does can be manually tedious, instead of just writing, doing this, and just looking at that. Yeah. So that is what I feel. But that's like a personal opinion. Someone else will maybe prefer the other way.
So TLAPS, I think, is in the midst of a rewrite or something. Is that true?
Well, it's not really a rewrite, right? It's liveness. Reasoning about liveness is being added to TLAPS, and that involves changing some of the existing code, obviously.
But it's currently it's obviously in a very usable state. You found it like fairly easy to onboard?
I don't think it's. I think it's pretty, because this is actually an easier proofs. I've done one which is of a different an executable code, and I translated to TLAPS, and I proved even that. I found it pretty reasonable to use. But you have to be patient and methodic with it. Yes. In fact, while I was doing that proof, I realized that there was a safety violation in that code, the executable code, and I caught it while I was writing the proof. But people had ran simulation tests on that proof, did stress testing, they couldn't find it. Some students had also done model checking of it, and during the model checking, they couldn't find any issues. But
you found it with a proof?
Yeah.
That'd be interesting.
Yes. Because the way that bug manifests, it's very complicated. It's very, it takes a lot of states, and so that sense, it is pretty, it can be pretty difficult. But again, those students, they were not using like Azure servers or something to run the model checking. They were doing on their local servers. So
how large would the finite model have to have been in order to encounter this thing you found?
So you will have to the thing you have to do, basically, someone has to first do phase 2A, then someone else has to start phase 1A and do phase 2A, and then this guy has to again do phase 1A, phase 2A on a different ballot. And then after all of that, when chosen happens, then you can prove that that's unsafe. So the whole pipeline should be just reaching phase 2B would take 4 actions. But if there are acceptors, so it would, if there are, say, 3 acceptors, so to reach chosen for even from starting from one phase 1A, it would be phase 1A, then 3 phase 1Bs, then phase 2A, then 3 phase 2Bs. So even reaching 1 would be 8 states, 8 depth, but then that has to happen at least 3 times. So it would be 24 at least.
With 3 acceptors.
With 3 acceptors, yes. Yeah, but we always have at least 3 acceptors. Mm-hmm. So that's the smallest case. 3 acceptors and 2 values.
So actually, this Paxost spec, is it very difficult to model check even with 3 acceptors then? Like I guess it monotonically increases or something, does it?
Yeah, but that's also, I don't think that's an issue because even the other spec is the same because the send is, I didn't change the send and message, so they also have it. It's just that those have aggregate queries and there they have derived variables. So that is the ease that has.
But I'm just interested, so with 3 acceptors, you would be able to find the thing you found with TLAPS if you let it run long enough. But that would be how long do you think? Crazy amount.
That has to be, yeah. It also depends on the machine and how cloud services and stuff. Yeah. Maybe if you use it on a cloud server, hope that should do it. But again, it would be pretty tough. It would be remarkable if TLC can find that bug. Because
one
trick that could be done is or maybe more than a question. So what you can do with TLC, you can obviously guide its path, what it's checking. Prior to finding this bug, do you have any kind of idea that this would be a corner where there are some?
Absolutely not.
Okay.
It looked, the code looked extremely innocent and it looked that it's completely fine. But then I was trying to prove it, and I couldn't prove one step. And then I just started decomposing and write more and more. And then at one point I reached one line and I realized that the whole thing is wrong. Yeah. Yes.
Prove something that's false.
Maybe going back one step, you said TLAPS is very mature, not mature, but very usable. So how much time did go into the actual writing the proof?
For the bug one?
No, for
this one?
Yeah.
Oh, this was nothing.
Just to give an idea, right?
Oh, this was, I think, 1 day. That's it. For the history variables? Yeah, just 1 day. Yeah. Okay. But that's kind of deceiving because I already had the proof from the olds. So I already had an idea of what the proof would be. And then I also had all of the history stuff and the method. So I knew that, I have to prove this, and it would.
Similarly, let me rephrase the question. How much the ratio of time that goes into actually encoding the proof? What do you think is the ratio between finding the elective invariant and so on?
I think, once you find the invariant, that's the tough part. We're talking about history or in general?
Yeah.
In general, again, the toughest thing is how do you get the invariant? Once you do that, you have an idea of what the proof would look like. So that would be 1 day, assuming you have the invariant and you can get the skeleton out in 1 day at most. But then to actually prove it, if everything is just numbers and sets of numbers, that shouldn't take you like one more day, I think. But when you have functions and sets of records, then that can take you a week to, it can take you a week to figure out all the, at most. Yeah. Yes.
So I'm curious about the error you found with TLAPS. Just like, so this was in Leslie's spec or what?
No. This was an, it was an executable code of Multi-Paxos, which was written by my advisor, and she wrote it as a, it's influenced by the Multi-Paxos code of von Renesse and Altebuchen, which they had written in, I think, Python. But that's one of the few public Multi-Paxos executable codes. But what my advisor was trying to do was write it in Distalgo and as a case study and see how it's very compact and everything. So she thought she wrote the right thing, and it looked right. Even when people stress tested, they couldn't find anything. But then, yes. So it's not on Leslie's. It has nothing to do with Leslie at all.
Implementation of Multi-Paxos.
Yeah.
That was slightly incorrect.
Yes.
Okay, I guess we have to take the remaining questions offline because we have to get out.
Yeah.
So thanks again.
Yeah.
Thanks.